Hello. So, we are continuing on with our work in probability, and again we're on Texan Test 5 now. We're in chapter 2 of probability, and we are going to be looking at testing for independent events or testing for mutually exclusive events. So I'm going to remind you of the significance of independence and mutually exclusive. So independent events are events that do not affect each other. So we've been looking at that fairly recently. So events that don't affect each other, if I flip a coin and roll a die, they have no effect on each other one way or the other. So the outcome of one doesn't affect the outcome of the other. And when that is true, when we know we have independent events, the probability of A and B happening, often written as the probability of A intersection B, like in set theory, is equal to probability of A multiplied by probability of B. Now that is only true for independent events, events that don't affect each other. Now what is always true is the kind of generalized version of that, which is the probability of A given that B has occurred. So the probability of A when we know that B has already happened is equal to the probability of A and B divided by the probability of B. And we looked at where this formula came from a few days ago. That's independence. Now, mutually exclusive means two things cannot happen together. Both things cannot happen at the same time. So, in the situation where we have mutually exclusive events, events that cannot happen at the same time, we'd have the probability of A or B is going to be equal to probability of A plus the probability of B. In set notation, A or B is usually written, or is always written as A union B. Now the version of that is always true, and this is another formula you need to know by heart, is going to be the probability of A or B, probability of A union B is equal to the probability of A plus the probability of B, what we had up here, minus the probability of A and B happening together. Now, how this links into our tests is if the probability of A intersection B is equal to the probability of A multiplied by the probability of B, then we have independent events. If this is equal to A multiplied by probability of A multiplied by probability of B, then we must have independent events. Or another way of saying this, slightly less obvious that it's saying this, but probability of A given that B has occurred is equal to the probability of A. So saying this in English makes it fairly obvious why it would be a test for independence. What is the probability of A if B has occurred? Is that the same as the probability of A in general? If those two things are the same, that means the two events don't affect each other, the two outcomes don't affect each other, therefore they're independent. So this is a fairly, for me anyway, this is a way of explaining it to myself that it works quite well. So if the probability of A given B is the same as the probability of A, they must be independent of each other because the fact that B has happened has not had any effect on A. Now that's the two ways of looking at tests for independence. The ways of looking for mutually exclusive events are, is the probability of A or B, probability of A union B, equal to the probability of A plus the probability of B? If that's true, they must be mutually exclusive. Or, put another way, is the probability of A and B happening together equal to 0? If that's equal to 0, that means they must be mutually exclusive. And a reminder again that mutually exclusive events can be spotted very easily on a Venn diagram because there's no overlap. There is no intersection of A and B, therefore they are circles that are totally separate from each other. There is no overlapping area between A and B if they are mutually exclusive to each other. Now, let's continue on with a little bit of a practical example, but I'm not going to say anything here that isn't really covered already. So if I have my Venn diagram in question 2, I event A and event B. I have probability of A only happening is a quarter, probability of A intersection B is 1/12, and probability of B only is 1/6, and I have probability of a half of neither of them happening. So again, this is one of the versions of Venn diagrams that we can come across, and we're asked in part 1 for the probability of A. Now, under exam pressure, there is a danger that students will make a mistake and they will just write down a quarter. Everything inside this circle is inside of A. So there's a probability of a quarter inside of A, and there's a probability of a 1/12 inside of A. And when we add those two fractions together, we get a third. So be careful of that. If it asks you about stuff involving A, everything in A must be included, so all of the stuff inside the circle A. Likewise with B, probability of B is all of the probabilities inside of the circle B, so a 1/12 plus a 1/6. And that ends up being equal to a quarter. So now I have the probabilities of A and the probabilities of B. Now show that A and B are independent. I'm going to go and do this two ways. The first way is I know that the probability of A intersection B must be equal to the probability of A multiplied by the probability of B if they're independent. So let's check if that's true. Probability of A intersection B is equal to a 1/12, and the probability of A intersection B, and the probability of A multiplied by probability of B is equal to a third multiplied by a quarter is equal to a 1/12. Now the next bit you must write down. Therefore, as probability of A intersection B is equal to the probability of A multiplied by the probability of B, this implies independence. You must write this line down, or an equivalent to it. You must explain to the examiner that you know that because these things are equal, the events are independent. Now, the next point is, the other way of doing that, because we need to know this formula by heart, I'm going to remind you of this formula, and we're going to use this method of checking for independence. So we're looking at probability of A given B would be equal to probability of A intersection B all over the probability of B, which would be equal to probability of A intersection B, the 1/12, all over probability of B is a quarter. If I'm dividing by a fraction, I invert and multiply. A very important method that we need to remember. And that gives us a third, which is equal to the probability of A. Therefore, I would write this down, an equivalent argument here. Therefore, independent as probability of A given B is equal to the probability of A. So the fact that B has happened has had no effect on the probability of A. Now, question 5 on the same page is a lot briefer, but I wanted to talk about it. A and B are two independent events. If probability of A is equal to 0.4, probability of A union B is equal to 0.7, use the formula that to find B. Now the last line of that they wouldn't necessarily give you in an exam question. They might, but they're not required to, because you will recognize that as our general addition rule as our mutually exclusive equation. So you're required to know this formula by heart. And as such, they could ask you question 5 without giving you that formula explicitly. So why did let's write down what information they've given us. We have probability of A is equal to 0.4, probability of A union B is equal to 0.7, and we are asked for the probability of B. Now we can see we should be able to sub into this formula up here to make some progress, but we don't have enough information. We want to get a formula that only involves probability of B and numbers. So this is our problem piece. So I'm modeling how we would approach this in an exam. So we have lots of information for this equation, but we don't have enough. This specifically is our problem. Well, is there any formula or any fact we know about probability of A intersection B? And then we look at the question and it says, given that A and B are two independent events, well, what do I know about probability of A intersection B if we have independence? Well, that means that it is going to be equal to the probability of A multiplied by the probability of B. And that gets us out of our problem, because now we can write an equation that only involves probability of B and numbers. So union B is equal to probability of A plus the probability of B minus the probability of A multiplied by the probability of B. Now I can sub in what I know and solve. So 0.7 is equal to 0.4 plus probability of B minus probability of A is 0.4 multiplied by probability of B. Doing a little bit of subtracting and rearranging, I get 0.3 is equal to 0.6 probability of B. Divide both sides by 0.6. To get probability of B by itself. And I get a half is equal to the probability of B. So in an exam, you can see how you would approach that question. Write everything you know down, see if there's anything that it stands out to you as, I don't want that in my final answer, this is preventing me, and see if you know any formulas that would allow you to make progress. And that's what we need to be able to do for now.